Welcome to SERVOsoft, the optimal solution. This tutorial demonstrates SERVOsoft's master follower feature, and together with the Optimizer Pro, will be used to minimize cycle time for a 3-axis gantry robot, while maintaining the position relationships with each axis. What is the master follower? The master follower is a virtual axis, which all other axes in a system follow, based on the position of the master. The reason it is so powerful is because it allows for changes to a multi-axis system by only changing the master axis, which all other axes are defined by. So, increase or decrease the master velocity, and the follower axes increase or decrease their motion profiles, all while maintaining the position relationships with the master, and also with respect to each other. In this tutorial, we will showcase the master follower's abilities by using it to identify constraints in our robot system, by defining a max stop event with just the master axis, and by minimizing the robot's cycle time while maintaining the position relationships with all axes. Let's get into our first objective. The master follower can be enabled in this power group by changing the sequence type from time to master follower. I'll make a copy of this power group before doing this. The 360-degree modulo distance defines the master axis as one 360-degree rotation. What you'll see as we move into the charts for this power group is that now all other axes sequences are defined by the master's position. Therefore, by default, the chart x-axis is the master position in degrees, and not time. Since the master follower has a constant velocity, position is mapped directly to time. Of course, there is the option that time can be charted on the x-axis instead of the master's position if the user wishes. This next part relates to defining a max stop event, something we'll talk more about at a later point in this tutorial. Essentially, what this means is that once again, the follower axes are defined by the master's position, and the master must ramp the machine down to a full stop when a max stop event occurs. We'll define this ourselves later on though, so for now I'll click no. Now that the x, y, and z axes are defined by the master, I can now change one value, the master's time per rotation, and find where my limiting factors are in this power group. For example, if I change this value from 5 to 4.5, I can now see that my z-axis is approaching 90% utilization, and make changes accordingly. I can now go into the z-axis and see that my gearbox is the limiting factor, with an 89% utilization. If I open the chart, I'll just focus on the second move, since this is what is causing the 89% utilization. You can see that I need to find a way to decrease torque or acceleration and increase speed, since in this move, the gearbox does not reach a very high speed. I can now go into the z-axis and open the second move. Here, I will decrease the acceleration to get more speed, and I can do that by applying the 1/2 motion rule. You'll notice as well that the available torque decreases at this part of the cycle, since I've increased my speed. If I now go back to this gearbox, I can see that I've dropped its utilization by nearly 20%, and now the motor is the limiting factor. I can now keep identifying bottlenecks on various axes as I decrease my time per rotation by just altering the master axis. Now we've completed our first objective, using the master follower to identify constraints in our robot system. Now that we have a better idea of how the master follower feature can be used to affect multiple axes by changing just one value, let's use this knowledge to define a max stop event in the whole system by just using one axis, the master. A max stop event is defined by ramping the master down to a velocity of 0, so that when a max stop event occurs, the entire machine ramps to a full stop. If I now click this max stop button, SERVOsoft allows me to copy the sequence profiles I'm using in this power group into a max stop sequence, so that I can now define this event. Here, along with the master's velocity, I'll show the energy and the bleeder power in the z-axis to best identify where to begin ramping down and for how long. If I go into this sequence, I can split the master cycle into 3 segments. It seems as though the energy is greatest at around 1.62 seconds, meaning this will be the most difficult place to stop, and it should be where the ramp down begins. I'll make my first segment this length. Now, I can set the last segment to dwell on just the master follower, and all other axes will dwell. Finally, I can create a ramp starting at the same velocity in the second segment and going down to 0, and once again, all other follower axes will ramp down. Since I have a bit more room until my bleeder power enters the margin, I can decrease the time of the second segment even more. We'll try 125 milliseconds. As you can see, the bleeder power is now much closer to the margin. Now that I'm showing the other axes, you can see that they are all ramping down to 0 during the second segment because they are all following the master's ramp down to 0. Now, we've completed our next objective, to define a max stop event with just the master axis. Let's move on to minimizing cycle time using the Optimizer Pro. The Optimizer Pro is a powerful optimization tool, which allows for the optimization of one of several target functions. For example, to optimize for time, this tool will play with several different values and bump up against several limits, such as torque, power, speed, accel, and jerk, as it works to reduce cycle time. Now that this system is defined by the master follower, we can enable the Optimizer Pro to optimize for the master's time, and it will affect all of the follower axes. Before I do this though, I'll create another copy of the power group and label it variable 2 segments. I'll ensure that the sequence type is variable, and now I will split the master up into 2 segments. I'll open the Optimizer Pro by clicking the button at the top. The optimizer must work within limits and constraints, so the user can select the Suggested Parameters button on the side, and the program will automatically create these constraints. Note that these are just suggestions. You can keep them, change them, or remove them entirely based on your discretion. You can also see all of the parameters you are about to enable here by clicking the drop-down arrow. I'll walk through them each one by one. The poly 1 to 5 parameter creates a fifth-order polynomial on the 2 segments which is continuous in velocity and acceleration. Recall that a spline is simply 2 or more polynomials strung together that are continuous in velocity and acceleration. The reason a 7th-order polynomial isn't used in this case is because while it is very flexible, it tends to create more swings and reduce the efficiency of the optimizer. The algorithm settings determine the step resolution for duration, velocity, acceleration, and jerk. Smaller increments create a higher resolution, but can add to the runtime in finding the optimum. This is a good example of where you might want to override the suggested values. Since this application is very sensitive to changes in the profile variables velocity, acceleration, and jerk, I'm going to increase the resolution of these step values. The max and feasible solutions in the algorithm settings determine how many incorrect solutions the optimizer will go through with each population value before it gives up and moves on to another population seed. The constraints tell the optimizer to play with various values, such as velocity or jerk, within the given range and step resolution. Finally, the additional constraints are listed below these. StartVal equals EndVal ensures the velocity is continuous, meaning it ends at the same velocity it starts with, and the same is true for start and end accel. Here, this acceleration constraint is very low, which limits what the optimizer can play with when only using 2 segments, so I'll change these values to -800 to 800 degrees per second squared. Spline distance overshoot allows the optimizer to change the distance of each segment within a range of its original value, but ensures that the total distance of every segment still adds up to 360 degrees. I'm also going to add a speed margin to provide the allowable speed range for all motors in the power group. Finally, the power group utilization ensures the utilization of any component in the power group does not exceed 90%. I will click Start to run the Optimizer Pro. It will take a few minutes to run, so I'll pause the video and come back when it's complete. The optimizer has found a time of 4.097 seconds, reducing the time per rotation by nearly a second. That's an 18% improvement. You can see here on the chart that the optimizer reduced time by pinching the torque profiles of each axis using the max torque at various moments throughout the cycle. If you were to run the optimizer again to try to get a better result, you could split the chart into more segments. I'll do so by creating another copy of the power group. Often, the best places to split these segments are where there are multiple swings in the chart that are not very close to bumping up against the max torque, or there are multiple pinch points in one segment. In this example, you can see several bumps at the end of the first segment in the X and Y axes, and many in the Z axis at the beginning, so I can split this into two. There are also several pinch points and bumps in the second segment, so I'll focus on splitting this up as well. Keep in mind these are just judgment calls. I'll continue to do this for the rest of the profile. Now, I can go back to the Optimizer Pro and, using the same parameters, run it again to see if there is any improvement to the cycle time. I'll pause the video until this is done. As you can see, the optimizer has found a new cycle time of 3.883 seconds. That's a 22% improvement. Now, we've completed all of our objectives. We've used the Master Follower and Optimizer Pro to identify constraints in the robot system, define a max stop event with just the master axis, and to minimize the robot's cycle time while maintaining the position relationships with all axes. If you were to complete these tasks without the Master Follower, you'd have to create ramps and run the optimizer on every single axis in the system. But by using this feature, you can achieve great results quickly and efficiently. This concludes the tutorial on the Master Follower with the Optimizer Pro. Thank you.